Okay. Well, so this is a short course on lunar volatiles, as I hope you all know. And basically this is part of a larger study on new approaches to lunar ice detection and mapping. And so there's two main aspects to this. One is the sort of scientific background. Why are we interested in volatiles like water on the moon, and whether or not they can be found as in the form of ices at the poles. Then there's also an exploration aspect in terms of the types of missions that we might design now and in the future to explore for volatiles on the moon and potentially utilize them as a resource. So today's short course is divided up into a few different sections, and I think the first part of it is sort of a little bit of background on the science and the basic principles of how volatiles get trapped on the lunar surface and other airless bodies. And you'll see that temperature is a fundamental aspect of this. And so our first two talks before the break are going to be given by my two co-leads, Andy Ingersoll and Dave Page. And Andy is going to lead off with a talk on volatiles on airless bodies.
Well, I'm going to do what professors often do, which is to talk about something they don't really fully know anything about. But there's advantages to that. You get to sort of approach each facet of your subject with equal ignorance. You're not biased towards anything. And also, it's kind of fun to review a field. I've written maybe one paper, which I'm going to actually talk about in about a minute. Not in a minute, but for a minute. And it's only worth about that much. But I am going to try and cover that subject up there. And I decided to make my outline in matrix form. You think of a talk as being sort of a linear thing, but just for fun, I decided to produce a matrix. And I produced the matrix first, and then I started filling it up with slides and material later, and I realized that life is not as simple as this matrix. I thought I would do the following. I'd say, okay, whoa. Let's go down this column, which is the subject of volatiles delivered by comets and asteroids, and what kind of volatiles are delivered. If we could sample the ices at the poles, we would be learning about composition of comets and asteroids and maybe their rate of impact. What good would they provide? Well, maybe this would provide life support or power and propulsion. So the matrix sort of breaks down here because sources cut across all of the three sources. The moon's interior is a source of volatiles, and the solar wind is too. But let's keep going down my naive organization down this column. When a comet or asteroid hits the moon, it doesn't necessarily land in one of these cold traps, so you've got to get the volatiles there, and there's a gauntlet that the volatiles have to run, and I was going to talk about that as if it was a separate subject. And competing with the volatiles trying to get to the cold traps, or not trying to, but randomly getting there. The gauntlet is the solar UV is going to ionize them or dissociate the molecules. Once they're there, they can sublime and sputter. So I was going to talk about that separately, and then talk about water from the moon's interior, which seems to be hydrated minerals that get outgassed. Well, this is sort of an anomalous in my matrix structure, but the basic physics is what's the moon doing with water anyway if it formed from a very, very hot impact. And then unscrambling what we might find, we have to decide how much of the water and the minerals of the moon, on the surface of the moon, is actually due to endogenic sources, or what fraction is maybe from somewhere else, exterior. And finally, the solar wind, protons hitting the oxygen in the soil are going to make water. And if we could somehow sort out the contribution of the solar-derived volatiles over time, we could learn about solar activity versus time, possibly cosmic rays. But that record, dating back to when the sun was maybe a different kind of producer of stuff, has to compete with the degradation of the record, and maybe it's preserved by burial, who knows. So that's my matrix. It's going to turn out that it was a naive concept to think that I could go down each column separately, because they're all mixed up together. So you could probably start this earlier than Watson, Murray, and Brown, but a lot of people started there, and this is Caltech, and these were Caltech authors. Before there was a planetary science department, there were a few planetary scientists, and Watson, Murray, and Brown wrote this paper, basically focusing on the sublimation rate of a frost exposed on the surface. This is the vapor pressure of that frost. This is its temperature. This is the gas constant. That's the molecular weight. And the important thing is that the rate of sublimation into vacuum is proportional to the vapor pressure. And the vapor pressure is an incredibly steep function of temperature, as we all know. So this is 1 over T, and this is the log of the evaporation rate in centimeters squared of water for this curve per centimeter. It's the number of molecules per centimeter squared per second. And here's 10 to the minus 20 in those units. And just for your information, the age of the solar system is 1.44 times 10 to the 17. So if your temperature is so cold that you're on this part of the water curve, you're going to be losing a lot less. I'm sorry. This is grams per centimeter squared per second. You're going to be losing a lot less in the age of the solar system. You're going to be losing a lot less than a gram per centimeter squared. So that's a millimeter, fraction of a millimeter. So Watson, Murray, and Brown really focused on the sublimation. This formula actually appears in James Jean's Dynamical Theory of Gases, 1904. Let me just say, since I am ignorant about every slide that's going to be up here, I want you to interrupt, and I'm going to ask for help at certain points. I'm going to reach a point where I'm going to say, well, what did the experts say? And I'm going to say, well, you're the experts, and so I'm going to do that. It turns out that they should have worried about other processes besides sublimation, or in addition to sublimation. There are many ways that a molecule can get lost in transit to a cold trap, or while it's in a cold trap. Micrometeorites can are energetic enough to sputter molecules off. High energy photons can sputter them off. And well, that's probably enough for right now. Okay. Now, I'll start off sort of moving historically. This is also a Caltech JPL group, Slade, Butler, and Mulliman, used goldstone as a transmitter of, I think this is 3 centimeter radar waves, circularly polarized, and they used the Very Large Array as a receiver, somehow synced up, and they got these images of Mercury. Now, this will be your first quiz question. What's the really interesting thing about this picture? You got it right there and right there. That is the interesting thing. And so what happens is they send this circularly polarized light out there, and if this was an ordinary type reflection, it would reverse its direction, but the spinning of the, if as viewed by the transmitter, it would still be a clockwise spin as it came back to the transmitter. That would be what a specular reflector would do. But if it takes a tortuous path through the medium, it can come back, the word is depolarized, with both senses of circular polarization. And actually the reverse sense came back a little stronger, but only from this region. If they had shown the specular reflection, you would have been blinded by the spot right in the center. But looking at the unexpected polarization, it brings out scattering media, and the key is multiple scattering inside the medium and several scattering events inside the medium. So it's got to be a fairly transparent medium. And water ice is the only substance at that time that they knew that did this. Other ices do it to a lesser extent. And so that they wrote a paper published in Science entitled something or other, Evidence of Water Ice on Mercury, at the poles of Mercury. Then along came, so that was 92, and Dave Page wrote a paper in 92, I wrote a paper in 92. And the question is, what kind of craters are going to be the coldest? Well, if you think that a nice deep crater is going to be the coldest, you might be wrong. Actually, it's more likely to be the flat craters whose depth to diameter ratio is small, provided they are just barely deep enough to have permanently shadowed places on them. And the reason is that if you have a larger depth to diameter ratio, the walls keep each other warm. But if you're very open, as long as you have a shadowed region, then that shadowed region, that permanently shadowed region, will be colder. And that's shown here. I apologize for the fuzziness, but this is such an old paper that I couldn't get on to the, from my home last night, I couldn't get on to the proper, clear archive. So here's a depth to diameter ratio. This is latitude on Mercury, 76 to 90. And this is depth to diameter rate, and these are temperatures along here. And so these are depth to diameter ratio of 1 to 5, and here's 1 to 16, and here's 1 to 40. And these strange lines like this. So let's just think of the 1 to 40. That's a very low relief crater. It's got a depth diameter of 1 to 40. And if you're at whatever this latitude is, below that latitude, there are no permanently shadowed places at all in that very flat crater. Now, if your depth to diameter is 1 to 16, you can have permanently shadowed craters down to this latitude, and then it shoots up to very warm surface after that. But in this region, real close to the pole, very flat craters, you can get really low temperatures, 50 Kelvin or even below. This is sort of an arbitrary cutoff at 112 Kelvin, but it corresponds to an evaporation rate using that formula from Watson et al. Of 1 meter per billion years, which presumably is a pretty low evaporation rate, but you could decide on any other limit that you want. It's not an absolute cutoff, it's proportional to the vapor pressure of the fluid. Now my little contribution was to do the math for a spherical bowl-shaped crater where you can get an exact answer for the temperature of any permanently shadowed placed in the spherical bowl-shaped crater. And this is, and you can get an exact answer, but this is not the formula. It's a little too long to put on this slide. This is in the limit of a very small depth to diameter ratio. Little d is depth, big D is diameter. And I show this formula just to show you that the temperature goes down as the depth to diameter ratio squared goes down. And that's pretty much borne out by this more detailed calculation that Dave Page did for more realistic crater shapes. Okay, we're still. Now, next person who came along also in the 1990s was Brian Butler said, well, let's ask how many molecules, if you release a molecule at an arbitrary point on the surface, how many molecules will make it to the cold traps? What fraction of them? He said, well, what's hindering them? And it's mainly photodissociation and photoionization. And that is a parameter of his model. That means to be a tau, but it got turned into a t. So with a little bit of study, he decided to choose these 3 values for the lifetime of a molecule in empty space at the orbit of Mercury, 3.3 times 10 to the 4 seconds, 6.7 and 13. So a day is somewhere in here. And so that's, the molecule has to get to a safe place in a day or even less before it gets photoionized or photodissociated. Now, photoionization is probably going to be the end of it because it'll get swept away by the solar wind. Photodissociation, maybe, maybe not. It has a chance of recombining. Even ions have a chance. The OH ion has a chance of recombining. But he just put a parameter in here, which is that lifetime. And then he did a random walk, just release molecules, huge numbers, hundreds of thousands of molecules, and let them hop around on the surface. Each hop leaves the surface with a Maxwell-Boltzmann velocity distribution. I think he assumed no bouncing that they rethermalized each time, and each time they hit the surface, they start off with a new, totally random Maxwell-Boltzmann distribution. There's a small amount of loss due to escape, gravitational escape the planet, but mostly it's photo-associated ionization. Okay, and the particles were spread uniformly across the surface, and he just let it rip. And here's the percentages that make it into the cold traps. With a shorter lifetime, fewer molecules make it. Longer lifetime, they stand a better chance of hopping around and making it to the cold traps. Now, this is from his paper, and I really had a lot of trouble understanding this figure, so I generated my own. This is Brian's caption. This is the contribution of each latitude in 1 degree bars to the eventual buildup of molecules in the cold trap. And you say, wait a minute, why should 89 degrees contribute less molecules than the equator? They should have a much better chance of reaching a cold trap at 89 or 90 degrees than these guys. And so I struggled with that. And then I said, wait a minute, it's because there's just less, since they're uniformly spread over the surface, there's less territory between 88 and 89 degrees than there is between 1 and 2 degrees. And so I said, I'll take that into account, and that generates this curve, which is the probability of a single molecule starting at various latitudes reaching the cold trap as a function of its starting latitude. And this is a much, to me, you don't have to like this, but to me, this is a more intuitive curve. If you start out really close to the cold traps, you're much more likely to make it to a cold trap than if you start out at the equator. But nonetheless, despite this gauntlet that the particles have to run, they do make it from the equator as well as from the pole. All right. Yeah.
Does that take into account the temperature of the equator versus the poles?
Yes. Butler has a diurnal cycle and temperature versus latitude and all sorts of good stuff. Now, then along came Julie Moses, and she accepted Brian Butler's fractions, those percentages that make it to a safe landing, and then she said, what kind of impactors are likely to be the big contributors to the cold traps? And she didn't consider all impactors. Well, she considered Jupiter family comets, those are in red, Halley-type comets in blue, and asteroids in green. And these are very logarithmic scales here. So this is the mass of the object, and this is this is another sort of Monte Carlo thing. Since we don't know all the orbits of the Halley-type comets or all the orbits of the Jupiter family comets, you have to do some kind of statistics about it. Their initial orbits and how many of them are out there, and how many asteroids are going to come in and strike the moon, or Mercury in this case, I'm sorry. these stars, I don't fully understand what these stars are, but they are the biggest contributors. These are powers of 10. One notch here is a power of 10, and these are the biggest contributors. And the bottom line, which I do understand, because it's in words, not this figure, is that the biggest objects are contributing more mass than all the gazillion little objects. So the big objects are, even though they're not as many, they make up for it. And those are statistically the most uncertain because they involve big asteroids and big comets coming in. And also, naturally, the big objects have a lower collision probability, but there they are, contributing the most mass. And here are some numbers from Moses. There's no at all from Moses' paper. Asteroids, quite a spread, because the statistics are bad when you're talking about a small number of big objects, and whose orbits we don't know in advance. But something times 10 to the 17 grams over 3.5 billion years. That's a quote from her paper. Jupiter, well, both kinds of comets, similar number, except the spread is even bigger. Something times 10 to the 17, even maybe 10 to the 18 grams over 3.5 billion years. Then, this was not really a topic of her paper, but independent other estimates of micrometeorites, which are interplanetary dust particles, similar number. And at the time of this paper, there were at least the radar observations, Slade et al., who had estimates of the amount of volatiles that were actually there, and it was comparable to these numbers. So obviously, this is a hard thing to do because you have a little dot, and you have to decide how much water is there. The idea, really big objects will produce an atmosphere on Mercury, and then the molecules will start pushing each other out rather than just individuals hopping out. I didn't see anything, any discussion like that in the paper. So I don't know how big an effect it is. So this kind of hangs together as theoretical efforts often do. They often match the observations, maybe sometimes having done theory for the wrong reasons, I would agree. But it's good that you can at least get in the right order of magnitude on the amount of volatiles at the Mercury pole. Now, I'm going to tell you, and you probably already know, that the poles of the moon are likely to have 100 times less volatiles than Mercury. And that's still a mystery. So we'll get to that. And that's where I'm going to ask for help. Tell me, solve the mystery. Okay, so let's switch over to the moon. This is from Feldman et al. And I can't remember what the name of the spacecraft was. Lunar Prospector. Epithermal neutrons sample deeper, maybe down to a meter of regolith. They're more penetrating than the fast neutrons. And I'll show you fast neutrons in a minute, but it's just absolutely clear that something's going on at the poles. This outer circle is 45 degrees latitude, and this one is minus 45 degrees. And these are some kind of projections on the poles. So purple indicates more absorption going on of these epithermal neutrons than you would get from mere soil, and it's the hydrogen atoms that are doing the absorption, so purple means hydrogen atoms. So it's just that you see less, you get a lower signal when you have the hydrogen because they're absorbing the neutrons. Now the fast neutrons don't show that same kind of signal. So here's a different way to look at it, also from Feldman. Here's latitude starting at 0 degrees latitude. There is the equator. These are the epithermal neutrons again. Going up to the pole, there's 90 degrees. Going over the pole on the other side, and here's 270 degrees, which is the same as the other pole. And you can see the absorption of the neutrons at the poles here and here of the epithermal neutrons, and sort of a background continuum where there are apparently not much or no hydrogen. I think it's no hydrogen. Now here's the fast neutrons, which, as I said, sample not as deep. And the poles really don't stand out in this figure. The conclusion is that it's a mixture of soil and ice. And in fact, their best estimate, sort of combining these two data sets, is that these polar deposits that have ice in them, clearly they have some ice in them, they have some hydrogen in them, and the hydrogen means at least hydrated minerals or probably ice, but that ice cannot be pure, at least in the top meter of the surface. It can't be pure. It can only be of order 1 or 2% relative to everything else, which is soil. And if there is pure water ice, it's got to be below the level where the epithermal neutrons are sensitive, which is 1 meter below the surface or deeper. And this is where that estimate of 2 times 10 to the 15 grams in the total reservoir at the poles comes from. And that is this number here, which is 2 orders of magnitude less than Mercury. And that's weird. Mercury has an obliquity, remember, relative to its orbit, its spin axis is just about 90 degrees. So it's that zero obliquity is 90 or 0. Let's call it zero obliquity. Is that right? Yeah. Yeah. Zero obliquity is favorable for having permanently shadowed craters, but the moon is only, I don't know, 1.5 degree obliquity. And really, they should have comparable numbers of craters. It's not clear that Mercury gets more bombarded than the moon or less bombarded. It probably gets more solar wind, but asteroids and comets, who knows? So this is a mystery. And I'd love to hear the solution to that mystery. Okay, let's move on here. What are these lunar, not Mercury, what are these lunar deposits made of? Well, lacking a instrumented rover with or a sample return mission, you throw a big inert thing at one of these deposits and see what comes off, and you detect it spectroscopically. This is microns from 1.3 to 2.3. And you get these spectra. So here's the model. Well, the data are there, and there's the model fit, and these are various gases. And I must say, I'm impressed that they can pull out some of these numbers with all this kind of stuff. But here are the numbers. Water, it's the main constituent, but there's several percent of a lot of other things. CO2, H2S, whatever that is, methanol. What is that? Methanol. And some organics. I hope in this short course or in our studies later, someone's going to tell us what it all means, this mixture of stuff. Is this what a comet or a spent comet looks like, or a carbonaceous chondrite meteorite, or what do these mixtures of molecules, what are they telling us about the sources, or perhaps about the sources and their rate of destruction? Now, obviously, with these spectra, you're not going to detect noble gases, but as we're going to learn, there are places on the moon where it's cold enough for organites to sit there for a long time. So if we knew what these compositions of these lunar ices were, what would we know if we knew the composition? Beyond just tabulating it, what would we say? The solar system works like this and not like that. Speaking of hydrated minerals, thank you. There was a long standing assumption based on early analysis of lunar samples that the moon was totally dry, and that didn't inexorably point to a very hot formation scenario for the moon, but it helped that idea along, I would say. This is my reading of the literature over the weekend. That if you had a giant, a Mars-side object colliding with the Earth, you would have magma particles or even rock vapor sprayed out into low Earth orbit, and some of that stuff, all of that stuff would be so hot that it would lose its volatiles, and some of that stuff would reaccrete in orbit and escape, and go into orbit rather than falling back to Earth. And that stuff that remained in orbit, having been devolatilized by its high temperature, became the moon. And so the failure to detect, water or OH in the lunar samples was a sort of confirmation of that idea.
It wasn't detected, it was just felt to be.
Contamination. Yes, that's right. And here's really an answer to the contamination question. These are glass beads, and this is distance in microns from the center of the bead. So this is the center of the bead. There's the surface of the bead. And with the kind of instruments that are available in 2008, Saal et al., they were able to sort out where the volatiles are. Here's chlorine, sulfur, fluorine, and water here. And there was more of these volatiles near the center of the beads than at the surface of the beads, and that's opposite to what you'd get if it was terrestrial contamination. If it was terrestrial contamination, it would be the other way around. The surface would be contaminated, the center of the bead would be more pristine. And so this was a big deal. I just from the number of papers that quote this solid all paper, it's clearly this changed a lot of people's thinking about lunar hydroxyl or lunar water. All right. Then people started looking at different minerals. And I don't quite know why apatite is a special thing. It's a sort of a calcium phosphate with its crystal structure has usually fluoride or fluorine, but that fluorine can be replaced by chlorine or OH. And this is some of the results from Greenwood et al. Although I pulled the figure out of a review part. I like this review article by Vasilevsky, by the way. Recommend it. I'm not giving you the reference, so you'll have to figure that out. But this apatite, which, well, the only thing I do understand about apatite is that it's a sort of an end member of magmatic differentiation. So as a magma cools, a lot of other stuff crystallizes out, and the last little drop of magma, or maybe not the last drop, but right at the end is when the apatite comes out. So it's a concentrator of volatiles as a magma cools and crystallizes. So here's what you get. You get really close to weight percent of water in this apatite. That's a lot. And that, if the general lunar basalts had that kind of weight percent water, no one would have claimed terrestrial contamination. But here's the deuterium to hydrogen ratio in units of delta D. So 0 is standard mean ocean water, and this is parts per thousand. And mid-ocean ridge basalts range sort of from 0 to minus 100, which would be minus 100 parts per thousand would be like, what, 10% or something. So they range in this narrow range, and these lunar apatites are way up and down. And again, I appeal to you experts. I don't think that's been solved, why there's such a huge range of deuterium to hydrogen ratio in these lunar apatites. Remember when I showed you my second slide with that matrix outline? That was kind of my summary for this whole subject. Not at all, thank you. All of these sources are hard to separate when you have them all piled up in one cold crater. And if we knew everything we wanted to know about that crater, every composition, even layering, we might not know what we really want to know. It's a tough subject, this thing. Even if you take the measurements, how do you interpret them in terms of the history of the solar system or whatever? One more slide on volatiles in the crust of the moon. These are melt inclusions. Now, I'm not a petrologist either, but a melt inclusion seems to be, you have a crystal, which is the outer matrix or the mantle, but inside there's I guess it's a glassy little thing that never segregated, it was there before it got this crystal forming around it. So it's a rare beast, but it tells you about the composition of the original magma, or it tells you it's closer to an original magma. It doesn't have this differentiation that goes on when you crystallize a magma slowly, piece by piece, and wind up with apatite at the end. This is a much more better sample, even though these are very small things, of what the original melt was. So, here you have water parts per million, and these are these circles with, this is water versus fluorine, and water versus sulfur, and water versus chlorine. These are, parts per million. These are the original melt getting up to 0.1%, I guess in counting, not in mass, but nonetheless, these are, this is pretty wet for the moon. And at least Howry say that, well, this implies that the volatiles were not entirely lost during this lunar forming giant impact. Or else maybe right after the impact there was exchange of volatiles between the Earth's atmosphere and the stuff that eventually became the moon. But it does change, having lunar magma with these kinds of water abundance or volatile abundance does change the nature of our interpretation of the lunar forming giant impact. By the way, these circles here without the black rims are the matrix in which these inclusions are embedded, and they are dry. Okay. Now, I've got a few more here. Another kind of water on the moon, it's everywhere. And this too had been, this is spectroscopic evidence. This is 3 microns right here, wavelength, and this is 2.8. And these little dips, which are a function of latitude, I'll mention that. This is from Carly Peters. These, I guess, had been brushed aside as contamination of some sort, and you needed a lunar orbiter with a spectrometer, near-infrared spectrometer, to really believe them. If you look at lunar samples in these spectra, you of course can brush it away as terrestrial contamination. But now we're looking from an orbiter at the moon itself. And the interesting thing about these water absorption features is that they're a function of latitude. So the higher latitude, the deeper the absorption feature. And if you're at the equator, there is no absorption feature. So, but there is absorptions at all latitudes, right? Right, here's the 18-degree latitude line. So this is stuff that's everywhere, even though it's a little bit more dense at the poles. And that's not all. It's a function of daylight. So it's an inverse function of daytime. This is a good figure if you can read it. This is the depth of the, this is a different instrument on a different spacecraft, and Sunshine is the author, and it's just coincidence that she discovered this effect of sunshine. But down means a deeper absorption in the 3-micron band, which means down is more water. And so let's see if we can read this. Here's the morning. Here's noon. So that's less water, because down is more water, deeper absorption. And then afternoon, it begins to, water begins to reappear, and then you come back to evening, and the water has reappeared. So it's a...
There's a controversy with that, and whether thermal emission contamination is decreasing the apparent dance.
Okay, 3 microns, you're normally, you think you're looking at reflected sunlight, but there is at 3 microns a component due to thermal emission, yes. Okay, good to know.
Jessica knew that too. She's not stupid.
Yeah, no.
Disentangling the contributors to the signal is difficult.
Yeah, these are not, yeah, I mean, you've got a lot of, these are not such deep absorptions, 0.9 to 1. Okay, now I couldn't find quantitative estimates. Julie Moses did and other people have done quantitative estimates of the delivery of volatiles, and coupled with Brian Butler's running the gauntlet percentages, so they've done quantitative estimates of how much volatiles are coming from asteroids and comets and interplanetary dust particles. I couldn't find any comparable numbers for the 2 other possible sources. The solar wind, which is obviously capable of making water. When a hydrogen atom hits an oxygen atom, you can make water, even if the hydrogen is charged, and you can still make water. So I couldn't find any quantitative estimate for the solar wind, and I couldn't find any quantitative estimates of the contribution from the endogenic lunar water in the soils to what might wind up in the cold traps. And I didn't dare do the second one, but I did do a totally back of the envelope, uncertain by 3 orders of magnitude calculation for the solar wind. I went to the Wikipedia.
We got, what was a liter per football field.
No, I didn't use those units. I did go to the Wikipedia to say, what is the solar wind flux? And they say, well, it's variable because you have an active sun in it. So I took some Wikipedia number of 3 times 10 to the 8 per centimeter squared per second for the particle flux in the solar wind at the moon. And I said, well, let's just assume 100% efficiency so that every particle in this solar wind that strikes the moon, take the moon's cross-sectional area, no, every 2 particles, because it's H2O, it makes 1 water. How much mass? Huge amount. It's 100 times the asteroid plus comets, and it's 10,000 times the observed polar ice in the moon. This is Julie Moses's number, which has huge error bars, but not 2 orders of magnitude. And this is the Feldman et al. Number of what's observed. And so if you had 100% efficiency, which is highly unlikely, you'd have a big contribution from the solar wind. Yes, this stuff is going to be produced right on the surface. It's going to be very vulnerable. If the sunshine daylight effect is true, then it doesn't last long at all. The sun comes up, it heats it, and disappears, or it goes somewhere. Well, maybe it'll hop around until it reaches the sun. Now, I know nothing about this subject, but it's the ISRU people, in situ resource utilization. And there is a paper I read by Sanders and Larson, and I pulled a figure from their paper about what resources, what would you do with them if you had some lunar volatiles. Well, I think one of the things you'd do is you'd separate the water into hydrogen and oxygen. You'd have a rocket fuel. The water, if you could purify it from all those, methanol and so on, you could drink it. The hydrogen you could breathe. I'm sorry, the oxygen you could breathe. Makes propulsion. And then with a real power source, you could do mining, you could build structures, you could build your spacecraft and not have to lift them off the surface of the Earth. I'll let someone else worry about that. And this is my final slide. And my only point is the point I already made. All of these processes are mixed together in these lunar polar traps, cold traps, and it's going to be very hard to unscramble them. That's it.